So this is our last official lecture. I have decreed that lecture 46 will be the end. What better day than Cinco de Mayo? All right, so that said, I will not have an official Zoom thing on Thursday or Friday, but we'll talk more about that in a second. But more importantly, I want you to understand that the final will be posted by tomorrow morning. As I said, everything, and it's due a week from tomorrow, so May 13th. By midnight, and then your grades are due from me to the university Friday the 15th. Excuse me, my nose is running. A couple of things that I want to point out. I've gotten some emails and I don't know if any of you particularly said it, but I've had enough that it needs pointed out. So you're all aware at this point that the university has this pass-fail grade option if you want it. You don't have to use it. It's there if you want it. And the important thing you need to realize about it is you don't need to decide until after you see your grade. So you get to see what your grade is, and then you get to decide if you want it. Keep it or just take a pass or a fail. Does that make sense? I hope.
How does that affect your GPA?
Well, it doesn't. I mean, you don't get it. It doesn't help. It doesn't hurt. You just get the credits.
Okay.
Now, those of you, depending on what kind of program you're in. So, for example, if you're in like an engineering program or certain health science things, particular any of our programs that have an articulation with another school, you know, whether it's pharmacy or engineering or something, you need to check with that program. For example, in engineering, they're not going to accept a pass-fail. You have to have a letter grade for this class. And I'm assuming that's for most programs. So you need to double check that before you go and do any pass or fail. But again, the key point is next week, I'll submit grades. You'll get to see what your grade is. Then you get to decide if you just want to pass or a fail. So, does anybody have a question about that? Comment? Okay. Great. Okay, so what do we want to talk about today? Well, before we talk about, we have a short topic we'd like to discuss, and then we're going to call it a semester. But does anybody have any questions about any math or any homework that they want to discuss or anything? Yes, no, maybe? What in the heck is going on? You guys are sounding. Is everybody all right? I got all kinds of noise. Okay, so let's do a couple things, and then we'll have your final exam will be up for you tonight or tomorrow. Hopefully tonight, but I don't want to guarantee it. And then you'll have a week to do it. Hopefully everybody gets an A. Hopefully. Okay, so we're moving away from the idea. We spent a lot of time studying series, and so our next topic is sort of a transition to higher math, particularly those who will be going to Calc 3. I know many of you won't, but many of you will also be taking physics and other courses that will use some of these ideas. So what is this topic called? It's called parametric equations. So here's the motivation. The motivation is as follows. So what have we studied so far? So far we've studied curves given by a function. And a generic way to write a function is y equals f of x. I mean, you've been doing this since you first encountered coordinate systems. You know, let's just to beat the dead horse, what do these creatures look like? You know, y equals 3x squared minus 5, you know. Y equals sine of x plus e to the x, etc. These are examples of algebraic equations. They're examples of functions, and you guys know that you can graph and represent these functions as some curve in the plane. Now, turns out that there are some limitations to this description. So oftentimes,
can last slide, please?
Sure. Yeah. Sorry about that. Let me know when you're ready.
You can go ahead.
All right. So here's what we want to do is oftentimes we require more info. Now that might not make any sense, but imagine this. So for example, suppose we might want to imagine an object moving. So suppose, let's think of a very simple physical scenario. We have an object and we want to imagine it's moving along a curve. Maybe we want to imagine an ant walking across a floor, or we want to imagine the flight path of a bird, or we want to think about what happens to a charged particle as it comes in contact with another charge. So we want to imagine we have an object and it's moving. And if we want to study its movement, that would mean we need some sort of direction. So the question is, how do we assign direction? So let's just draw a picture, for example, of what this might look like. If I just have some curve, am I going this way along the curve? Or am I going the other way? So is this the start? And is this the end? Or is it the opposite? So does anybody have a question about what I'm using arrows to represent direction? Am I moving in one direction or am I moving in the other direction? Any comments, questions? Okay, so we want to ask ourselves, how can we do this? And it turns out there's a very, I don't want to say simple, but there's a very natural way of doing this. And the more you know about, say, vectors, the easier it is. And some of you know a little bit about vectors, some of you don't know much at all. So we kind of want to avoid that description right now. But sort of the notation might, we use might lend yourself or lend it to, so that if you know a little bit about vectors, it might make some sense of what's happening here. So here's the idea. So one idea is to imagine the object at some point in, say, time. And so to emphasize this, or to do this, we introduce a new variable called a parameter. So let's call it, for lack of a better word, t. So if I have some curve, let's imagine that this curve is in the xy axis. So let's just pick a couple points here. I'm going to circle these dots. So again, imagine we're in the xy plane. And so let's call this point x of 0. Let's call this y of 0. And I'm emphasizing that these coordinates x and y depend on some specific time. Call this t sub, k, and then this comma y evaluated at t. Well, I'm squeezing it in there. Let's put it over here. So this is some point x comma y, and let's call this maybe t sub 1, y evaluated at t sub 1, and then this could be x of t sub 2, y evaluated at t sub 2, etc. And then this could be the last one. So in general, what's a point look like? It's some point x of t comma y of t. So as t ranges, the point moves along the line. So you might not see that right now. We're going to do an example to help illustrate this in a second. Does anybody have a question so far? Okay, so let's do an example. For an explicit function, what does an explicit function look like? Well, that's the sort of the generic thing we wrote down earlier. What's an explicit function? Y equals f of x. We define a parametric curve, and it's typical to give it a name. We'll call it R of t. Now, what I'm going to write is going to look scary, but for those of you who know a little bit about vectors, it might seem, you might have an idea of where this notation comes from. So this is a lot of letters, and we know that when we're like in Calc 2 and we're not so used to all this abstract language, things get confusing. So we're going to do an example of this in a second. But essentially we're saying, instead of thinking thinking of this curve as, you know, x comma f of x, we want to think of it as the x and the y coordinates both depend on some parameter, some other variable time. So before you get too overwhelmed with this particular scariness, let's make a real useful connection right now, and that is the following. So here, t starts at some value, which we'll call a, and it ends at some value b. And for each t, x of t, or excuse me, let's just write it as, let's just get to the adult thing before we simplify again. So for each t, r of t gives the coordinates x comma y. So it's not going to make much sense right now until we do an actual concrete example and we see why this actually works. Okay, does anybody have a question before we do that? All right, so let's go to the next page then. And hopefully this will make the previous page, maybe I should have went this way first before I wrote the scary stuff down. So I'm going to write R of t equals t comma t squared. And I'm going to say, okay, let's assume that t goes from 0 to 2. So what I want to do is I want to imagine, let's start t at 0 and let it go to 2, and let's see what we get. So one way to do that is to make a table. Let's pretend we're back in middle school and we're learning algebra and graphing for the first time. So let's make a little chart. Of values. And so what I want to do is I want to ask what happens with t here. So let's make a t column. Let's say 0 and then a quarter, a half, and 3/4 and 1, and then just go to 1/2 and then 2. And let's ask what is the x coordinate, what is the y coordinate, and then what is the actual point. Well, of course, notice our x coordinate. Let's be very clear what's happening here. The x coordinate is just, this is our x of t. And then this guy is our y of t. So the x coordinate, because of the way I've defined this parametric equation or this parametric function or description, they're all just the same. This is 0, 1/4, 1/2, 3/4, 1, 3/2, and 2. And then the y is the corresponding, what happens when we square t? Well, we get 0, 1/16, 1/4, 9/16, 1, 9/4, and 4. And then we can fill in, you know, I guess I don't really need to do this column because I really just did it, but fill in all of these. And if we connect the dots, just like we did when we first learned how to graph, we get a nice, pretty picture. And it's an old friend. Of course, I'm not drawing this to scale, but that's okay. So let's imagine that we have a stopwatch, and I'm going to put my stopwatch on, and I'm going to hit go. And then what point am I at when t is 0? When t is 0, I'm here. So let's get a different color out. When I'm at 1/4, I'm here at 1/16. And then I'm here, and then as I keep going, I grow all the way up to here. So what I end up tracing out is this parabola. And by doing this with the t's, what we've done is we've given a direction to what's happening here. Because as we let t range from 0 to 2, this thing is moving up the curve. Does anybody have a question about this? What's also nice about these parametric sort of equations, or this parametric description, or the parametric curve, as I'm calling it, is that it allows you to assign or put speed inherently into this particular, into how we move along a curve. If I modified my x's and y's, I could traverse this curve with less than t ranging from 0 to 2. Maybe I have a question.
So in your previous example on the, I think it was like a page ago or 2 pages ago, those coordinates don't seem like they'd suffice. Like you just draw straight lines between them and you lose a lot of information. How would you go about?
Well, you talk. I'm confused. You talking about this right here?
Yeah.
Yeah, right. So again, you'd have to imagine I'm just drawing them very far apart so you can see what I'm getting at. But don't forget, t is a continuum. It's an interval. So you would have infinitely many values. Now, look, if you want to get into the philosophical argument about, well, you know, if you're talking about plotting it, look, okay, here, hold that thought for a second. Maybe this will help. Let's do another example, and maybe this will help clarify for you. So if I look at this, for example, I'm not just doing, I can't, you know, if I'm assuming that t starts at 0 and goes all the way to 2, I'm not ignoring all the numbers between 0 and a fourth. I just don't need to compute them all. I recognize there's a pattern. Do you understand what I'm saying? It's sort of like when you first learned how to graph a curve years ago when you were in algebra class. I mean, you would make this chart and then you'd connect the dots with a nice smooth curve. We know that there's a nice smooth curve between these dots as long as the function is continuous. Don't forget, we have information. We know that t squared is a continuous function. We know that its graph is a nice smooth curve. And we could tell you, in fact, Jeff, if you go way back to Calc 1, I know it doesn't seem relevant right now, but we can tell you exactly how steep the curve is at any point. How can I tell you that? Because I know what the derivative is, and the derivative tells me how steep a curve is. So if you go back to that page that maybe you were curious about, I think your initial point was, well, it seems like you were talking about maybe drawing straight lines between these points. You have to remember that x and y are going to be continuous functions. They're going to be descriptions, which means whatever they are, we would imagine that there's going to be a nice smooth curve. I just drew this generic curve for the heck of it, but when we do examples that are more familiar expressions like parabolas and what we're going to do now is a circle, it makes it a little more clear. And maybe this will help clarify your confusion right here. So I'm going to do this, and then if you have an observation or a comment, please let me know. So and this is one that you should be very familiar with, and I don't mean that you should already know it, but you should make it familiar. So we can parametrize a circle of, say, radius A with, how do we parametrize a circle? We use R of t equals R cosine of t, comma, r sine of t. So the way to think about this is you let t range between 0 and 2 pi. So now, Jeff, t is going to touch every single number between 0 and 2 pi, all of them, infinitely many. And when you do that, as you let t range, it's going to trace out a circle. So to help sort of make sense of that, let's draw our circle. How is this circle connected with this description? Would be the question we'd like to ask. Well, here's how. You know, let's just pick a couple points that we can easily compute in our head without thinking about it. You know, when t is 0, what is r of 0? R of 0 is equal to the point r, comma 0. So that's this point right here. Or excuse me, not r. I'm confused. I confused you guys. Hold on. This should not be r. I said radius a, so this should be the letter a. I apologize. Fix this. A, and then this is a. What about it say pi over 4? If I let t be pi over 4 and I plug it in, I get a times the square root of 2 over 2. And then it's a times the square root of 2 over 2. Now, if you graph that point, that's just right here. If I were to take r evaluated at pi over 2, well, the cosine of pi over 2 is 0, so you get 0. And then the sine of pi over 2 is 1, so you get a. So you're at this point. And so what we're saying is as t ranges all the way up to, say, 2 pi, when you get to 2 pi, you're all the way back where you started. So it brings you all the way back here. So this point right here corresponds to t equals pi over 4. This is the point t equals pi over 2. Over here, this would be the point t equals pi, etc. So we're working our way around the circle. Now, when you're in a pre-calculus course or maybe a trig course at one point, you hopefully would have learned about different properties of sine and cosine and how to change things like speed. You know, how can I make this particle move around faster or slower? So here's an interesting question that you might problem. So this is not okay. So this is just a circle, Alyssa. It's not the unit circle. The unit circle would have, okay. So let's clarify this. So here's some examples. The unit circle has the following parametrization. You can write this as r of t equals cosine t, comma sine t, where t goes from 0 to 2 pi. Or if you wanted, you can use this parametrization. You can modify it. You could say the cosine of 2 pi t, comma, the sine of 2 pi t, and this goes between 0 and 1. If you graphed both of these, they would trace out the unit circle. Of course, they're doing it at different speeds. Now, I can't really explain to you what that means until you start thinking about this. You know, you have to start drawing and sketching to get a feel for sort of what we mean by speeds. The thing I would encourage you to at least think about now is that as t ranges from its first point to its last point, what these descriptions do, these parametric curves, is they give us a sense of direction. They also give us a speed. So if you wanted to, again, if you wanted a more realistic example or something that we could use for a physical purpose. So this is an example you might want to ponder. I'm not going to pretend it's easy for us to make sense of it. So let's suppose we have this equation. So we have this curve. Let's say 4 cosine of pi over 15t, comma 4 sine of pi over 15t. And let's range t between 0 and 30. So I just gave you some parametric equation. And what this does, if you think about the properties of sine and cosine, and you put some specific values of t in to get a feel for what's going on, what I have is I have a circle of radius 4, and I can imagine some object moving around it. So what can this thing describe? Well, it could describe an object moving along a circle of radius 4 at a constant speed. In fact, what else can we say? The object makes 1 lap in 30 minutes. So here I'm assuming the units of my t are minutes. So again, let's ask ourselves, where is our object at the beginning of, let's start. Hey, where's the object at? When t is 0, if I plug 0 in, I get 4, 0. So that means I'm at the point 4, 0. And then as my stopwatch goes, my object starts moving around the circle. And when do I get back to where I started? I get when t is 30. Now, you might ask, where did that pi over 15 come from? Well, that comes from me understanding the basic properties of sines and cosines. Now, you might not remember those things, and that's okay, but this is an example that is designed for you to think about if you want to go back and you know, I don't want to say relearn, but think about those properties of sine and cosine. What does the, you know, again, these are things that were taught or should have been taught to you in a trigonometry class. But you should have studied properties of sines and cosines, like amplitudes and frequencies. And if you go back and try to sort of remember those things, you might have a better idea of where I got this pi over 15 business from. I know that's not the greatest explanation, but it's something that I would encourage you to do. Does anybody have a question about this? So if for those of you who take Calculus 3 and some other physics classes, you do a lot with these things. All right. All right, another example that is useful to know. So we've done a parabola, we've done a circle. Another example is a line. So how do we describe a line? What is a line? The line of slope b over a that goes through some point, let's call it x naught, y naught, has the following parametrization. So what is r of t? The first coordinate is you take your point plus a t, and then and t, of course, ranges between a line we imagine goes and extends forever. So t can just range from negative infinity to infinity. Again, what happens when you plug t equals 0? And when you plug t equals 0, and you just get x naught, y naught, which is the one point it has to go through. Now let t range, and you'll see this indeed does get the job done. And so, believe it or not, there comes a time when it's more useful to write a line like this than it is to write it as y equals mx plus b. Okay, does anybody have a question about this? Going once, going twice. All right. All right, so a closely related topic, and this is going to be the last thing we talk about, and we'll touch it briefly right now. And some of you may have seen this before, is what's called polar coordinates. So a related topic is what we call polar coordinates. So here's the idea. The idea is typically we have a point in the plane. We call this the XY plane. Typically, this point is denoted by how far it is from the horizontal axis. We'll call this x sub 1. Call this y sub 1, just to be clear. And so this is what we call Cartesian or rectangular coordinates. And instead, what we'd like to do is we'd like to say, okay, maybe we have a better way of telling you where this point is located. And so another way, an alternative way is, okay, this is x comma y, but let's note that if we draw a line from our point to the origin, I can draw this line right here. If I do that, this makes an angle with the horizontal axis. We'll call it theta. And then also I can drop a perpendicular so here I have a triangle now, and I notice that this guy, this distance, which I'll call r, is the length of that purple line. And so using basic trigonometry, we can locate this point. So the point xy, so this can be associated with what we call r and theta. Again, for any xy I give you, you can compute what r and theta are. How are they associated? Well, that's just elementary trigonometry. Let's draw another picture and let's see. Well, we don't even need, well, okay, let's just draw one on the other page just to see what's happening. How are they associated? Well, if I draw this picture bigger this time, here's my xy. If I take this purple and draw a line. So if I make this triangle, then I can say some useful information. This distance is r. And if this is theta, what can we say about this particular thing? Well, what is the sine? The sine of theta is the opposite over the hypotenuse. So the sine of theta is y divided by r. The cosine of theta is x divided by r. So remember, this distance right here is y, and this distance right here is x, provided this is perpendicular. So what do? We give these names. So we call r, what is r? R is the square root of x squared plus y squared. And theta, which is the inverse tangent of y over x, we call these the polar coordinates of x and y. So what is the connection with this in the parametric thing? Well, there's a couple ways to do that, but notice that the x and y are given by r cos of theta and r sine of theta, respectively. And so what polar coordinates do is they take the plane, and instead of thinking it as a rectangular grid, it gives us a circular grid. So what is the polar or the rectangular or the Cartesian coordinate system we have? We think of this as like an XY axis. Well, that's a bad line. Hold on. What we can imagine is we have this rectangular grid. Use a different color. Right? This is what the Cartesian coordinates do, is they give us this, you know, like you've seen before, like graph paper, perhaps. Ooh. So why does it do this? Well, again, let's remind ourselves of what's happening here. If I have some point right here, we know that this is the distance. That's its y, and then we know that this distance is its x. That's how we're referencing its place in the plane. Now, what polar coordinates do is they do something completely different. They say we're not going to use rectangles to measure the geometry. So in the polar coordinate system, you use circles. I mean, that's sort of the idea here. The idea is that they're all concentric, but it's not always easy to do that. And so we use these things along with these lines, these what do we call rays. And instead of having rectangles, we have sort of these polar rectangles. So how is a point located? A point is located by its distance from the origin and its angle from the horizontal axis. So how is this point located? It's located by whatever this angle is and whatever this distance is. So this is fun. So this is the polar coordinates. And it turns out that many things that we do moving forward are better described in polar than they are in rectangular. Why would this be the case? Well, I mean, that's for you to sort of come to terms with, but just imagine we use different coordinate systems to measure all kinds of different things. I mean, how do we measure the geometry of the globe? Well, you guys will learn from, or remember from learning in school, things like longitude and latitude. We use a different coordinate system. Does anybody have a question? All right, so you get to do calculus in polar coordinates. You'll learn about that in Calculus 3, but it's worth introducing now. And what I would encourage you to do is to think about the connection between these parametric equations and how are they connected to this idea of introducing new coordinate systems. So on and so forth.
So everything you can do on the rectangular, you could do on the polar?
Oh, absolutely, yeah. And sometimes it's easier and sometimes it's not. That's the point. Now, we're not going to get into that because we're out of time. But we can develop the notion of integration. You'll see more of that in Calc 3 than you do in this particular class. But yeah, one of the things that you should be able to do right now is, one of the things I could ask you at least is to convert from polar to rectangular and vice versa. But that's just an exercise in trigonometry. That's not a complicated thing. That's just drawing a triangle and solving it. And that's about it. So does anybody have any questions?
Is the polar like when you label like S and theta similar to like arc length?
No, not. I mean, arc length. Be careful how you say that. I mean, polar coordinates. Arc length doesn't care about what coordinate system you're in. You could imagine no matter what coordinate system you're in, you should be able to determine the length of a curve, at least if it's, a normal type of a curve. So it doesn't matter what coordinate system you do it in. What it will turn out, though, is that sometimes the math is easier in one coordinate system compared to the other. I mean, think about this. How would you describe a circle in polar coordinates? Don't overthink it. The equation of a circle is real easy now. It's just r equals whatever it is, 4, 17. So whereas in the rectangular coordinate system, lines are super easy to represent. In polar coordinates, it's very easy to represent a circle. And so lots of things that are curved, like circles and ellipses and spheres and all that kind of stuff, they are much easier to describe using polar coordinates often than they are with regular coordinates. Does that make sense? I don't know.
Yeah.
So again, we because of the way this semester ended up going, we didn't get to do as much of this as we'd like. It's not the end of the world. Maybe I can put an extra credit problem for you to do some research about it or whatever if you wanted to. Anyway. Questions, comments? A good way to get a feel for this is just Google polar coordinates or polar graph paper, and you get an idea look at some Google images and that kind of stuff. And yeah, you can also do calculus. I think, Daryl, you asked, but we just ran out of time. All right, and I didn't want to have a class on Thursday or Friday and teach you new stuff because you guys got enough going on, I'm sure, and you have other exams and stuff you have to finish amongst dealing with life. So, but feel free to learn about it if you want. Okay, any other questions, comments?
I have a few things, but it's not particularly related to class.
What's that?
I have a few things, but we can do it after class.
Okay, that's fine. Sure. Any other comments or questions? All right, well, listen, then I'm going to end this party. I wish you all luck on your exams and going forward this summer. Hopefully everybody stays safe, and thank you. Any other questions before I stop the recording? Going once? All right, well, guys, thank you very much, and good luck, and blow up my email if you have questions. All right, and it's stuff about like Alyssa, I know you email me about your grade. I'm getting there, hopefully. But no, yeah, can continue, blow up my emails. All right, guys, be safe and good luck, and thank you. Hopefully we learn something.